Okay, this is a lesson on 2.3.1, direct and indirect variation. Okay, so first I want to talk about direct variation before I talk about indirect variation, which will ultimately be the star of the show for this lesson. Direct variation is linear. So we talk about this relationship being linear in that as x increases, y is doing the exact same thing, it's increasing. If x was decreasing, the y values would also be decreasing. So the formula that goes with direct variation is linear. So you can see x is to the first power. So y equals k times x, where k is the constant that every scenario has in common. So we're going to do a couple of those scenarios really quickly. So for example, if x varies directly with y and y equals 72 when x is 9, I'd like you to find y when x is equal to 7. All right, so what we're going to do is first try to solve for what this constant is, because that's the one value that every single scenario has in common. So here's how we'll set it up, keeping in mind that y equals kx is our standard that we're going to just plug in and solve for any missing. All right, so here we go. So when y is 72, x is 9. So there's the plugins for x and y. So now the only variable is k, so I'm going to just solve for k. All right, no symbol here, so that means multiply. So how do I unmultiply? I divide. Divide both sides by 9. 72 divided by 9 is 8. So our constant is 8. So now I can use that constant to help me find out what y is when x is 7. So go back to my form, y equals kx, but now I don't have to use a k. I can use 8, as that is the constant that I found. And they told me, all right, find y when x is 7. So I'm going to plug that 7 in right here for x. So find y when x is 7. So y must be 8 times 7, 56. And this is ultimately my answer. And again, notice when x was 9, y was 72. If I decreased x from 9 to 7, my y decreased from 72 to 56. That's what I mean by direct variation. All right, now we're going to talk about indirect variation. Okay, indirect variation. This would be as x increases, y decreases. So no longer are we talking about a linear relationship. All right, the formula, you can see how it's different from direct variation. Y equals k divided by x. Now k is still the constant of variation, and x and y are our variables. Again, x and y, like in a function, the x values are the inputs, y are the outputs. So we're going to do an example so you can see kind of how this works algebraically. X and y vary indirectly, and x is equal to 4 when y is equal to 12. Find y when x is equal to 8. Okay, so right away, what we need to do is find what the constant is, because again, that's the one number that all of these scenarios have in common. All right, so y equals k divided by x, and I'm going to substitute in for this scenario that they gave us. 12 is the y, and 4 is the x. Now what I need to do to solve is to get rid of divided by 4, I need to multiply. I'm going to multiply both sides by 4. These cancel on my right. And 48 is my constant of variation. So now to solve for my scenario, I no longer need to use k. I can use 48. So y equals 48 divided by x. And it says, okay, find y when x is 8. So y when x is 8. Y equals 48 for my constant over the 8 that they told me about. So now 48 divided by 8, y must be 6. So hopefully you could see when I had x is 4, the y value was 12. And then we said indirect variation. So we increased the y value, we increased the x value from 4 to 8, and that forced our y value to decrease from 12 to 6. As x increases, y decreases. Indirect variation. The variables are doing opposite behaviors. Now I want to do a couple of application examples for you to help you with those. So for instance, number 4 is a great one. The frequency of a radio wave varies inversely to its wavelength. So right away we know that we're dealing with inverse variation. We are dealing with y equals k over x. And what I need to do is I need to define what the y and the x variables are. So I look through here and it says radio waves vary inversely to wavelength. So I'm just going to go in order. Okay, so I'm going to say y are the radio waves, frequency, and x would be the wave length. That way I stay organized, I stay consistent throughout this solving process, and I don't get anything mixed up. All right, so now they told me if the radio wave is 30 meters long, that's going to be wavelength. That's an x value. Put that on the bottom. Has a radio frequency of 1200 kilocycles per second. So that's going to be a frequency. So that's going to be a y value, 1200. And then again, the constant is the thing that I'm looking for first, so I could find the one number that all these scenarios have in common. So to get rid of this division, I've got to multiply and get my variable by itself. These cancel. And my constant is equal to 30 times 1200, which would be 36,000, and that's kilocycles per second. Now what I need to do is use that constant to help me solve for the scenario where I find the wavelength if the frequency is 900. I know my constant. I can rewrite k as 36,000, and I can now substitute in for my scenario. Again, they want to know what the wavelength is when my frequency is 900. So I'm solving for x if y is 900. So 900 equals 36,000 divided by x. So this can turn into a proportion over 1, and I can now cross multiply when I have a fraction equals to a fraction. So cross multiplying in order to get rid of these fractions, 900 times x is 900x, and cross multiplying to get rid of these fractions, 36,000 times 1 is 36,000. And so now to get x by itself, I would divide both sides by that coefficient 900. Those cancel, and I've got x is equal to 40. So the wavelength is 40 meters when the frequency is 900. So again, notice that the x and the y are doing opposite behaviors. So we went from a frequency in our first scenario of 1200 to a frequency of 900. So that made our x value go from 30 up to 40. So as the y value decreased, the x value increased. That's the important thing to keep in mind about indirect variation. Again, notice our setup here. We had the x and the y diagonal of each other. That's very important to make sure that we get that inverse behavior.